What do you do with the ring of charge if you want to find an electric field? Okay, so we have in this problem for AP Physics C, E, and M, we have a ring here. And this ring, this circular ring, is sitting flat in this plane right here. And it has a continuous charge distribution. So we're going to say that this entire ring has some charge. Let's just give it a charge, positive Q here. Okay. What we would like to know is at a point, this is going to be from the center of the ring outward. At a point, some distance from the center of the ring outward here. Oh, come on, work with me, computer. At this point way out here, what is the electric field? And that's kind of that's kind of a tougher equation, or tougher question for us to answer here. So how are we gonna figure out what this is? Well, let's think back to what we did for our arc of charge and go from there. We know that for this ring that we have, we know this ring, it is gonna have charge all throughout it, okay? So a tiny segment of the ring here is going to have a charge dq. And we know that this tiny little bit of charge dq is going to make us a tiny bit of an electric field. And if we take a look at this, let's just put a few things into this. We know that this circle is sitting at an edge of r away. So this circle itself has a radial value. We're going to call that big R. We're going to take this line running straight up to our point from the center of the circle. We're going to call this Z. It's kind of going away from the circle. That'll be our Z axis there going up. And this means that if we go from our charge point to the point out here in space we care about, this will actually be some radial distance. That's the actual radial distance of the problem. And what we're going to see with this radial distance here is that this radial distance, if I wanted to, because this is a right angle, I could actually rewrite it as r squared plus z squared to the 1/2 power. That's just right there the Pythagorean theorem, right? We're taking the values of two sides of the triangle, or the two legs of our triangle, r and z. We're squaring them, adding them, and then taking the square root to find our hypotenuse, which we're going to call little r here. What we're also going to see is that little r, well, rather little dq here, it's making an electric field that points this way. And if we think about this all the way around the circle, we can think about the other side of the circle is going to have an electric field pointing in a similar manner, but like this. And what we're going to see pretty quickly is that the left and right components are going to cancel one another out. In the end, all we're going to have are components pointing upward on this circle. We can add them together. If this is some angle theta on the inside here, that's actually equal to this outer angle right here. And if this is some tiny component of the E field, dE, that means that here in purple, what we have is a tiny component of the E field in the x direction, which we could actually just write as dE multiplied by the cosine of theta. So a very similar setup to what we saw with the arc of charge with this dE cosine theta. And we're going to see why that's so important just in a moment. Now, if what we're trying to do is a fancy addition of all of these electric fields, and actually what we know is that these are all going to be electric fields in this, well, I have it as written as the x direction here, but maybe it's better written as the z direction here because they're all going in the z-axis. If we want to add all of those up, we know that we really just need to integrate the electric fields and a cosine of theta term. Okay, so there's our electric fields that we're trying to add up, and we just want the cosine terms of them. So how are we going to go about this? Well, I cannot just add up tiny bits of charge. Remember, this dE here, if we recall from our last video, this dE here represents the kq, or dq this time, over r squared. So we're going to have something like k, which is 1 over 4 pi epsilon naught. We're getting to the habit of writing 1 over 4 pi epsilon naught instead of just k for Coulomb's constant. And then this is some tiny bit of charge dq over r squared. Now we're going to do a few things here. Notice this is little r, that's the radial distance. We have that radial distance written in a slightly different way. Okay, let's use it. And instead of writing dq, let's think about dq as being a tiny bit of charge density over some length here. So we're going to say that dq is equal to some density multiplied by some length. Last time we did this, we called this r theta I wrote ds here, but this could be a dl, however you want to write it, whatever. Last time we called this r theta. We're going to hold off on that for just a second, okay? We're actually going to kind of swing in a different direction here, get a different idea for our values, and see what kind of happens. Now, if we're, whoa, my computer's going totally bonkers. There we go, all better. If we take a look at this and just kind of rewrite it, let's rewrite this as the 1 over 4 pi epsilon, and then our dq is going to be lambda ds over, and then this r value is actually going to be the big quantity here, r squared plus z squared, and then it's to the 1/2 power given by what we had in the original equation over here, but we need to square it, so this is just going to be like to the 2 over 2 power, or we didn't have to write anything there, okay? Now, and then last but not least, we have this cosine of theta term that's popped up. Now, why is this so important that I just kept this as a ds right now? Well, because of this. Let's take a look at this cosine of theta term. Before, I kind of integrated over that cosine term, and I very well could here. I very well could. But I'm lazy, and if I don't have to really think about my calculus, I'd rather not. So let's not. If I look at my cosine here and I go back to the triangle itself, this cosine theta is using, while this theta up here, it's also the same angle down here. And I know cosine is equal to an adjacent side, that's z, divided by a hypotenuse, which is right here. So I'm actually going to get rid of this cosine term by writing it like this. I can rewrite this cosine term as saying cosine of theta is equal to z over r squared plus z squared to the 1/2 power. And if I put that in right here, what it's going to give me for my setup is 1 over 4 pi epsilon naught times the integral of lambda ds z, because that's in the numerator, and then in my denominator, I'm going to get r squared plus z squared to the, well, 2 over 2 plus 1/2 is going to be 3/2 here. So r squared plus z squared to the 3/2 power. And that's why, especially in your math classes, writing things to like a fractional exponent is very, very helpful, because now we can start doing weird things like this. Now, if we take a look at this here, lambda is a constant, z is a constant, r is a constant, z once again is a constant. I can pull them all outside of this integral. So let's do that. I'm going to get lambda z over 4 pi eps naught times this giant quantity here, r squared plus z squared to the 3/2 power, and then I'm just integrating ds. Let's actually think about, like, what did we mean by that ds again, or dl if you're using that? What do we mean by that? Well, we meant that we're taking small segments around the loop, and we would like to know what is the entire length of the loop. You know what that is. This is a circle. What is the length or circumference of a circle? It's just 2 pi r. So what we're actually integrating here on is we're integrating from 0 to just the entire length of a circle, 2 pi r. And when I integrate this, the integral of ds is just s. It's probably the most straightforward integral you can get. And then whenever we put in our bounds, we're just going to get a 2 pi r out of that. So I'm just going to have here lambda z times 2 pi r over 4 pi eps naught times r squared plus z squared to the 3/2 power. Okay, and that right there will give you your electric field at a point in space. Oh, excuse me, I made a slight mistake here. I put a little r here just because I'm so used to doing that, but if we actually go back and take a look at our circle, we had a value for that r. It was big R. Whoops, don't make that mistake. Get your boundaries right, children. This is big R right here, so this will be big R in our final answer. So that's what's going on there. If you wanted to, like, you could leave it like that. But if you actually take 2 pi r and you multiply it by lambda, you're taking a linear density and multiplying it by a linear distance, and that will actually give us back for our circle the entirety of the charge positive q. So if you wanted to write this, and you'll see it like this in books, we could write this as, you know, q, or whatever your charge is, qz over 4 pi epsilon naught, and then r squared plus z squared to the 3/2 power. That will be your electric field due to a ring of charge. Okay? And we really didn't need any like true calculus to get that. We literally said, like, what is the circumference of a circle? It's 2 pi big R. And the rest was just clever geometries and understanding your algebra. So we're really just, like, once again, adding up pieces of an electric field. We're adding only the cosine terms of them up because everything else is going to cancel out due to symmetry of the ring. I'm thinking about adding up a bunch of little charges dq, but I can't add those. That's not a good calc method. So I'll integrate over some distance. In doing so, I find a lot of stuff kind of gets termed out, and I can pull it as constants to the outside, and then I just simply integrate the area of it, or the distance of a circle, the circumference of it, which is 2 pi r. And that's my final answer. So this, as soon as you see it, it's not that bad. It's really not that bad. We kind of know what we're doing here. There are a number of different questions that result in this on AP tests, so we'll go through some of those practice problems in later videos. But for right now, we're good, and this is finished. So adios, everybody. Y'all take it easy.